Welcome back to the channel. Today, I have the privilege to speak with Dr. Benjamin Jones, who is an associate professor of physics at the University of Texas at Arlington. He earned his PhD from MIT and specializes in neutrino physics, focusing on the nature of and mass of neutrinos, as well as the development of advanced detection methods for particle interactions. Hello, Dr. Jones. How are you?
Hello, pleasure to be here.
How's your Vienna trip?
It was great. It's my first time going to Austria, actually, and Vienna is a really beautiful city. And the conference I went to was really exciting. At the conference on advanced detector instrumentation, I got to visit the final resting place of Ludwig Boltzmann, who's the founding father of thermodynamics, who's buried there. So that was kind of a cool physics geek trip. It was great. Thanks for asking.
I visited Austria I think like 4 years back with my family. It was really beautiful. All right, let's start off with a few rapid fire questions to get to know you. Coffee or tea?
Coffee.
If you weren't a professor, what would you be doing?
I wasn't a professor. I would probably be working in finance, earning about 3 times more money and being about 3 times less happy.
Yeah, honestly, physics is just super fun. Early bird or night owl?
Both, but probably early bird.
Early
More.
bird. Marvel or DC?
So I said both to the last question. I guess I say neither to this question.
Oh, really?
I guess if I had to pick, I think Batman is DC, right? He seems the coolest because he builds cool things and then uses those to achieve his goals, which is sort of what I do. But I'm honestly, I sort of feel like many of the superhero movies just seem the same as all the other ones. Is to decide.
Yeah. What's a fun fact about yourself that people don't know?
Fun fact. Okay. I once tried to run to every subway station in London just for fun.
Wow. Yeah, I've seen people do that in videos. What's your favorite hobby outside of work?
I have a few hobbies, but one I really like is I go orienteering, which is, I don't know if you know what that is, but it's a kind of running race where you have a map and a compass and you have to find these controls that are like scattered around a forest, kind of running through the wilderness.
That sounds fun.
It's great.
Quantum mechanics or classical mechanics, which fascinates you more?
Quantum, it's easy.
Quantum?
Obvious answer, yeah.
Yeah, that's what I was thinking. Do you think time travel could ever be possible, or is it just sci-fi?
Well, I mean, in a sense, time travel is possible because we're traveling forwards in time all the time, right? And we've also learned that different people taking different trajectories between 2 different points can arrive having experienced different amounts of time passing. So, I guess in a sense, one of them has moved into the past from the point of view of the other one in that situation. So time travel in certain restricted senses is allowed, but it's not allowed if it violates causality.
What's your take on string theory? Promising or overhyped?
Probably more towards overhyped than promising, although it's hard to criticize it too hard because there aren't many other really viable models on the market for unifying quantum mechanics and gravity at the moment. So, I think of myself as a string theory critic, but I can't criticize too hard because I don't have a better theory.
Yeah, I tried learning it a few days back. It didn't make a lot of sense to me. Would you rather have a conversation with Einstein or Hawking?
Einstein. Hawking's amazing, to be clear, but Hawking did like one amazing thing and Einstein did like 5 or 6 amazing things, one after the other in succession. That guy was incredible.
What's the most mind-bending concept in physics you've ever encountered?
I think it's probably the many worlds interpretation of quantum mechanics. That's definitely the one that's caused me to do the most philosophical soul searching in my life.
Yeah, that one really threw me out. It was crazy. Now that we've had some fun, let's rewind in a bit and talk about your personal journey. Can you share your experiences growing up in the UK and how they influenced your career path?
Yeah, absolutely. So I grew up in a fairly small rural town in the UK called Hereford. There's really not much going on there. It's beautiful. It's got green rolling hills. There's a kind of cow named after Hereford. and it's got an ancient cathedral. It used to be important in the old days, but really nowadays it's kind of a sleepy, rural, middle of nowhere town. No university or anything like that. And to be honest, I really felt like kind of frustrated and caged in growing up there, and I was must be more to life than this. Um, and I suppose I think that drive to go and experience the world and to find out the bigger things in life has maybe contributed to giving me the drive that I've had ever since to try and pursue physics.
Have you visited back in the UK?
Yeah, I go back now and again. I mean, my family is still there. And so I see them ideally maybe once a year, something like that, travel back. The UK is beautiful and has lots of fun things to visit. It has history with a depth that America doesn't. And so you can go and see old castles and which is pretty cool. So I do always enjoy going back to visit.
What led you to pursue your undergraduate degree at Cambridge University?
Yeah, so I mean, I've always been excited about science, and even when I was very little, and I always did quite well in my classes and so on. And in the UK, like we don't have quite the same system of like Ivy League prestigious universities as you have in the US, but there's two kind of old prestigious universities in the UK, Oxford and Cambridge. There's kind of an understanding that if you do really well, those are probably the ones that you try and go to, right? So I heard that message. I mean, I'm the first of my family to even go to university, so I didn't really know what I was doing. But I'd heard that you're supposed to go to those ones if you're doing well. And so, I applied and got in. I almost didn't go, and that would have actually been probably the worst decision of my life to turn down that offer that I got. And I almost didn't go based because I sort of imagined that this prestigious university would be full of kind of rich, posh people who I would have nothing in common with because I'm just this like country boy, right? And they're from like rich families. And I came really close to turning down the offer from Cambridge, but luckily I didn't because, when I got there, I felt totally at home. I was like, oh, this is amazing. These are my people. These are people, they're not all posh, rich people. There's some of those people there, but they're not all those people. They're just really people who are brought together by like loving what they do and wanting to know more about the fields they study. And, that was something that from Hereford was quite alien to me, that those kind of people would exist. So when I got there, I was like, oh, this is amazing. And that's really what launched me on my journey to becoming a scientist, I think, was my experience in Cambridge.
How did your time at MIT shape your research interests?
Yeah, so MIT also, let's see, what do I want to say about this? So when I applied to MIT, I honestly didn't know that it was like a big deal place. I thought it would be kind of an adventure to go to America. And so I applied to American universities and some British ones for my PhD. And in the end, in the American ones, I just thought, what universities have I heard of in America that do physics? And so I applied to Berkeley, MIT, and U Chicago. And I didn't get into them, but I got into U Chicago and MIT. And then in the UK, I got into Imperial College London and Warwick. And thought, it would be exciting to go and live in a different place and experience a different culture and work with a different group of people. So I decided to go to the US. And then what made me pick MIT is that when I went there on my visit day, I met Jan Conrad, who was eventually my PhD advisor. And I feel like we really sort of bonded somehow over some common perspective that the important thing is to be creative and impactful, like have some real intellectual impact on the experiment you're working on and try and generate new ideas. Like it's not enough to execute somebody else's vision. You have to show up as a scientist and create something and make your mark on something. And I really felt like Janet and I sort of shared that approach. And it turned out she was a fantastic PhD advisor. So yeah, in terms of how MIT shaped me, I don't know how long you want these answers to be, but I'll keep talking until you stop me. Like, I don't know, in terms of how MIT shaped me, it's a very strange place. I mean, it's got a kind of like an intense nerd culture, like physics nerd culture and computer science culture and engineering culture and entrepreneurial culture. which is nothing like anything I'd experienced back in the UK. I mean, Cambridge has more of a sort of old towers of learning kind of vibe. MIT has this more tech approach where it's like build and code and develop and sell, right? And they're both super valuable contributions to my education, I think. I mean, I learned as much from one as from the other. And eventually my own personal approach is kind of a hybrid of the two. I think at MIT, I absorbed that culture in the first couple of years there. But then after finishing my graduate courses, I moved to Fermilab, which is the main particle physics laboratory in the US, which is in Illinois. So after 2 years of study at MIT, I then did the rest of my PhD in the Chicago area at Fermilab. And then I got a whole other group of experiences as well. So, you know, going to different places and learning from different people and getting a wide range of experiences really helps you grow as a scientist and develop all your skills, I think.
That's awesome. What inspired you to pursue a PhD in physics? Was there a specific moment or experience that sparked your interest in the universe?
Well, I think I've just always loved science. You know, there was a brief moment during high school when maybe I flirted with the idea of becoming a computer guy rather than a physics guy. But then I think I realized at some point that if you become a physicist, you get to be at the same time a computer guy, a math guy, an experiment building guy, a philosophy guy. You roll that all together into a package where you're using all those tools to understand the universe as deeply as it can be understood. And so, in a sense, all those things give you access to some kind of depth of understanding about the world. But it's really physics that lets you put them all together and apply them all as tools in this quest to understand the universe that we're in. So I think, you know, I don't know if there was a specific moment, but I've always been interested in science, and it gradually became pretty clear that physics was the way I was going to go. I mean, when I heard about special relativity and quantum mechanics, then I was locked in. Then there was no going back when I heard about things. Probably in like last year of high school or something like that is when I heard about those things. And I was like, oh my God, there's so much to understand here and I need to understand it.
Were there any challenges or obstacles you faced in your academic journey, and how did you overcome them?
Yeah, for sure. I mean, like there's probably too many to number, right? Everybody has challenges, and in a way we're shaped by how we grow in response to them, right? I think, you know, in a way, academic challenges are sort of boring to talk about, because academic challenges are like, I couldn't solve this equation, so I read a bunch of books and I learned to solve the equation, and then I could solve the equation. I mean, basically, academic challenges, you work hard enough, you solve them. The harder challenges are the personal challenges, right? And those are difficult because they hit you at random and they hit everybody differently, and you never know how they're going to affect you. I guess one of the things that was a personal challenge was, you know, when I moved to America, I, like, my wife and I had to live apart for a year, and that was a difficult time. And, you know, if there was anything that was going to get me close to dropping out probably from graduate school, it was the difficulty of us getting to live together. But eventually we solved that immigration problem, and she was able to come over and live with me in the US, and we've been married ever since. She's the love of my life. So we eventually solved that problem. But you know, it was a difficult year, and the thing that makes those problems difficult are not just that it's not just it's difficult to live apart, it's that you don't always know how it's going to end, right? You don't know whether it's going to be solved or how it's going to be solved. You just have to have that it is, right? In a sense, like that might have been one of my difficult personal challenges, which a lot of young people in science, I'm sure, have similar challenges to that and can relate. So I guess I want to send a message to them: have faith. It'll be okay. You'll figure it out.
Yeah, I can't imagine being away from my family.
Mm-hmm.
If you could go back in time, what advice would you give to your high school self about pursuing a career in physics?
Yeah, great. I have a very specific piece of advice for my high school self, I think, which is I would say it took me a long time to realize that ultimately the only person who is responsible for your learning is yourself, right? I think I had a tendency when I was younger to like blame other people for how much or little I was learning, or how bad or how well or badly I was doing, right? Like, it's like I sort of imagined that I had teachers and their job was to serve me stuff in a way I would understand. And if I didn't understand it, that meant they were a bad teacher and they weren't doing it. And I think what I gradually learned, I probably had this realization really like somewhere in undergrad when I finally found myself in this community of scholars that I'd never seen before. But really, the only person who's responsible for how well you understand anything or how well you do is you, right? If you don't understand something, you have to read it, engage with it, think about it. Like if you come against a new concept, like, say you learn about, I know you're interested in qubits, for example, right? Say you read about qubits and you're like, I don't really understand what a qubit is. I'd like to know more. The only way to know is to like get a book and read about it and then see if you understand it, do little thought experiments. Like what would happen if I did this and this? Can I figure that out? And if I can't figure it out, what would I have to do to understand the answer? Try and solve some problems that you make up for yourself, like test your understanding. And yeah, I think, I did learn that probably in my this is something probably most people learn during undergrad, I guess. I did learn it during maybe my third year of undergraduate, that ultimately it's up to me. But if I'd known that in high school, man, I would have like gone so much faster, like, and understood so much more, so much quicker.
That's an interesting philosophy. I haven't really heard that one.
Try it. You'll love it. You'll get so much smarter, so much faster if you approach life that way.
All right, now let's shift gears and talk about your research. Your work involves neutrino physics and astrophysics, two areas that are crucial to our understanding of the universe. Could you explain the significance of neutrinos in our understanding of the universe?
Yeah, absolutely. So, our understanding of the universe right now is really governed by two established theoretical frameworks. There's standard model of particle physics, which is basically a quantum field theory with a specified set of particles that are in it. And then there's general relativity that explains how space and time curve in response to energy in the universe. We don't exactly know how to put them together yet, but almost all situations, we know how to describe with one of those or the other one. And some very small set of situations, we can describe it with sort of a bit of both of them, like Hawking radiation, but almost explained with one or the other one. So the standard model of particle physics has 17 kinds of particles. 3 of them are these things called neutrinos. They really have to be there. I mean, the standard model is built on symmetries, and the symmetries tell you the neutrinos have to be there. You can't just take them away and have a healthy standard model without them. So they're deeply baked into our picture of how the universe works on small scales and in terms of quantum. Now, the reason that they're really interesting is they have very unusual and sort of superficially difficult to explain properties. They are super light. They're 1,000,000 times less heavy than the next lightest particle. They obey coherent quantum mechanics over thousands of kilometers in a way that other particles don't do. So they're these like really long baseline quantum interferometers. They are particles that may be made of a mixture of antimatter and matter together, something called a Majorana fermion. And they are also more numerous in the universe than any other massive particles. So that's really odd. And actually, it's that oddness is part of what gives us a clue to the role they're playing in the underlying structure of physics, even beyond the standard model. So the reason the research group cares about neutrinos is not just because they're intrinsically interesting. I mean, they're just interesting. But they're not just intrinsically interesting. They are a window through which you could ask questions about physics at higher energies and shorter distances than the other things in the universe. So what my UTA does is we try and use neutrinos to ask questions about why there is matter in the universe, or what is the nature of quantum gravity, or what is the physics that's at very high energy scales beyond the standard model. So we try and use neutrinos as like a keyhole through which we can see something about the bigger picture of physics beyond the standard model.
Yeah, first time I saw neutrinos, I thought it was like just like a random jumble of things. It was kind of confusing. Mm-hmm. What are the current challenges in detecting sterile neutrinos, and how does your research address them?
Sure. So I spent quite a lot of my research career so far looking for sterile neutrinos. I'm actually not looking for them right now. I'm giving that a break and focusing on some other challenges right now, but I'll probably go back eventually. But so sterile neutrinos are interesting. So often there's one of two reasons. So they're hypothetical to begin with. They haven't been observed definitively. There's a couple of reasons one might introduce a hypothetical particle into nature and try and look for it, right? One is you have a big theory that says this theory only works if this particular particle exists. So if you find that particle, you validate the theory, right? And that's how, say, the Higgs boson was discovered, that people had a theory of how the electromagnetic and weak interactions unify, a theory of how particles get their mass, everything fitted together. And if you saw this one weird particle that hadn't been seen, that would basically validate your understanding of all the rest of the theory. And then they looked for it at particle accelerators, they found it. That's amazing. That validated the structure of the standard model. There's another kind of particle that people like, another kind of way that people try and hypothesize about particles, which is that you have some data and the data doesn't seem to agree with what the current model says. So an example of this would be like dark matter, right? We have a model of how gravity works, but when we look at galaxies, they're spinning in a way that is inconsistent with our understanding of gravity. And it looks like there's other stuff in there that's causing gravity. And so there must be other particles in there somehow then that are causing extra gravity. If we understand gravity, there must be something new that's causing them to spin this way. And so then we'll have this idea there must be dark matter particles and we should try and look for those. So there's a group of scientists all over the world looking for dark matter particles to try and explain why these gravities are spinning weirdly. These galaxies are spinning weirdly. Now, sterile neutrinos are a little bit like that. So people have been doing experiments with beams of neutrinos, looking at how those neutrinos interact quantum mechanically, or how they propagate quantum mechanically and how they interact in particle detectors. And what they see in some of these experiments is some evidence that the neutrinos don't seem to be oscillating as they would. Oscillating means quantum mechanical flavor change. They don't going through that flavor change in the way that they would if there were just the three neutrinos that we know. And so just like in the case of the dark matter, you say, well, there must be something making those galaxies spin weird. In this case, people say, well, there must be something that's making these neutrinos oscillate weirdly. And so the sterile neutrino is one idea of what might be causing those weird oscillations. And so the first weird oscillations were seen in the 90s at an experiment called LSND, which was at Los Alamos. And there have been other indications of weird neutrino oscillations at the Fermilab experiments where I did my PhD. And the place where I contributed to this story was my team here at UTA used the IceCube South Pole Neutrino Observatory, which is 5,000 light detectors instrumenting a cubic kilometer of ice at the South Pole to study super high energy neutrinos made when cosmic rays hit the atmosphere of the Earth and look at how those neutrinos travel. And we tried to see whether we could see any anomalies in the travel of those neutrinos that would be consistent with sterile neutrinos. And so the first version of the analysis, we found no anomalous behavior. We found it was consistent with the standard model. And then we took 10 years more data and did the analysis again. And in that second, more powerful analysis, we perhaps see some kind of hint that there's some anomalous neutrino transport effect happening, which could be evidence for the sterile neutrino, although we don't have a very conclusive measurement right now. So, in particle physics, these measurements are very hard. They take teams of loads of people working full time, like some of the smartest people on the Earth, solving difficult problems to run these experiments. And so to do any one of those measurements is like a multi-year project. So I think I spent like 8 years working on sterile neutrinos and then decided, okay, I think I'm going to work on another project for a while. Given that I answered yes, and then I answered no, and then I answered maybe. So.
All right. You've been involved in developing barium tagging for Neutrino-less double beta decay experiments. Mm-hmm. How does this technology advance the field?
Yeah. So Neutrino-less double beta decay is currently one of the things I'm very passionate about. So the neutrino, as I kind of mentioned earlier, is a rare kind of particle in that it might be made of not matter and not antimatter, but something in between. The neutrino might be a kind of particle where when it spins around its axis one way, it behaves as if it's made of matter. And when it spins around its axis the other way, it behaves as if it's antimatter. And nothing else in the universe behaves like that. So it's actually kind of interesting because I mentioned that we use neutrinos to try and get access to these bigger, more profound questions about the universe. It turns out if the neutrino is a Majorana fermion, that can help us explain why there's more matter than antimatter in the universe today. So these deep cosmological questions, which we don't currently have an understanding of, which are really related to like, why are we here? These are big, big questions. So the only known way to tell if the neutrino is a Majorana fermion that we know of is to see this very rare radioactive decay, where a nucleus does 2 radioactive decays at once, but emits no neutrinos. And I don't want to go into the deep details, but this very, very rare radioactive decay would leave kind of a clear signature in our experiments, which is 2 electrons at a specific energy, and then a single ion of barium emerging from the decay of a xenon atom. So what my group, one of our main projects, and what I was in Vienna recently to present about, as you mentioned at the beginning, is to try and see if we can take tons of xenon gas and then those individual barium ions that are produced in those double beta decays. And if we can see a barium ion that's born in one of those decays, then we can say this decay definitely happens and the neutrino is definitely a Majorana fermion, and then we understand something really deep about universe and about the matter in the universe. So the way we're trying to do barium tagging here is that we're using organic chemistry. This is a technique from neuroscience, actually. We're taking techniques that are used for looking at how calcium is transmitted between neurons, and we're applying those techniques, which are based on creating organic chemosensors that sense barium. We're applying those techniques in nuclear physics experiments. And so I don't remember exactly what your question was, but I think that's more or less what you were asking, right?
Yeah. What are some of the biggest unanswered questions in your field today?
Okay. What is the connection between quantum mechanics and gravity? Why is there more matter than antimatter in the universe? What is the nature of physics on distant scales that are shorter than the ones that we can see with the current theories, like the electroweak scale or below? What is the role of the observer in quantum mechanics? Some people don't think that's an important problem. I think that's an important problem. And what is the nature of dark matter is another major unsolved question. What is the nature of dark energy? Why is the universe accelerating? What happened very, very early in the universe, like the first billionth of a second before the Big Bang? Was there a cosmological inflation? Yeah, that's a subset. Those are the ones most interesting.
Do you think any of these are going to get answered in our lifetime?
Yes. I mean, people often say that they think that physics is grinding to a halt because they look at the past and they see all these great discoveries that happened in the past, and then they're like, what has happened in my lifetime? But the funny thing is, like, when you look at the past, you're integrating over decades and then putting all that stuff together. Whereas, we're living our lifetime in real time. But even while I've been a professional physicist, I mean, we've discovered gravitational waves, right? We've discovered that the metric of space-time can ripple. Like in my lifetime, it was discovered that the universe is accelerating. And in my lifetime, it was discovered that there are high-energy astrophysical neutrinos being emitted from the center of the galaxy. I mean, these like big breakthroughs are like being made. And actually I said it already, but in my lifetime, the Higgs boson was discovered, which is the crowning centerpiece of the standard model of particle physics. So, and those things are not even just in my lifetime, they're in my professional physics career, which is not actually that long so far. So sometimes it's easy to fall into this trap that, things used to be discovered and they're not anymore. But we're looking back over a long period of time, and we're living this period of time one day at a time. I mean, profound things are still being discovered. So it's very, very possible that in our lifetime, a Majorana neutrino could be discovered. The nature of dark matter could be discovered. I hope for in our lifetime some progress on the observer problem in quantum mechanics. I sort of imagine with all this interest in quantum computing and quantum sensing, we will start to do even more fundamental work on quantum physics. That some genius may be able to crack that code, or maybe not some genius, maybe just some regular person who's thinking about the right thing at the right time, which is ultimately what most of the geniuses are, actually, as a matter of fact. Maybe he's different, but like people who have things named after them, a lot of them were just normal people. So yeah, I do think that many of these questions could be answered in our lifetime.
That's cool. Could you break down one of your research projects for us in simple terms? What was the
Oh,
goal and how did you discover it?
good. I also want to add one addendum to my last answer, by the way, just before I go on. I do think that these problems could be solved in our lifetime as long as we keep funding scientific research.
Yeah, that's a major problem, right?
Which is I do want to just say something briefly about that, because right now it seems like there is a significant fraction of the country who think that scientific research is a unnecessary expenditure and we shouldn't do it. Uh, and I think if we want to have progress on these things like understanding our place in the universe, but also practical things like understanding how to cure diseases and understanding how to solve the world's biggest problems, we have to keep funding scientific research. And so people should take seriously the idea that this stuff that we have could all go away, right? If we don't keep them. Okay, sorry, go to your next question.
Yeah. Could you break down one of your research projects for us in simpler terms? What was the goal and what did you discover?
Great. So which one do I want to break down? So I think that let me talk about my research project. Let me talk about my research project to try and do the barium tagging, because we've talked about that a little bit. So I've given some introduction. But so that was really the problem that I targeted as my first project as a faculty member at a university. So when you come to be a professor, right, you have basically 4 or 5 years to kind of prove yourself. So an office and a lab and a bit of money, and they say, okay, get some graduate students, do some research, and then we'll check whether you've really got the chops to be in academia and whether we're going to keep you. And then after 5 years, they decide whether you have tenure or whether they say, okay, you didn't, goodbye. And so, choosing what problem you're going to work on as a junior faculty member is kind of stressful, because you have to choose something where you both have a finite probability of success and it's also going to be exciting enough if you succeed that they will be past the threshold, right? So this problem, I mean, now looking back, it might have been a stupid decision on my part, because this problem that I chose was basically almost impossible to identify a single ion in a ton of material, but super, super exciting. And so, I picked this as my opening problem as a professor. And really to do this, I mean, I come from high energy physics background. I come from particle accelerators and neutrino interactions. I had no experience with microscopy, no experience with organic chemistry, no experience with ion beams. And in a sense, we had to learn how to do all of that stuff to try and build equipment to solve this problem. And ultimately, that was one of the most fulfilling projects I've ever worked on in my life. I mean, we learned all about how to do single molecule microscopy. We gradually improved the sensitivity of the apparatus to the point we could see individual ions of barium. And then we gradually developed techniques for moving the ions around and delivering to the microscopes. And then eventually, now we're at a stage where this technology is starting to look really real, like it could really be part of a particle physics experiment. And the next phase of my career now, what I'm trying to do is make that real, make that into a real experiment that can test for the nature of neutrinos. So it's been a real process of learning all these things from all these different fields and seeing the technology come together as we've innovated and combined things. It's been fantastic. And I should say that that's work that I've done with my students and my postdocs. It's not just me who's accomplished that. It's all.
Yeah. How do you use mathematics in your field? Are there any concepts that you think high schoolers should focus on to prepare for a career in this field?
Yeah. Well, math is a tool. And in our field, we use lots of tools, right? And different problems need different tools. So math is an important tool. Computer programming is an important tool. Building apparatus and using the scientific method is an important tool. Thinking deeply and conceptually is an important tool. And depending which problem you're going to work on at any one time, you'll apply different mixtures of those tools. So to be a physicist, yes, you need to be good at math. But you don't need to be like a prodigy at math. You don't need to have this like deep, abstract, incredible mind. You need to be able to use math as a tool. And so what I would recommend that high school students focus on in preparation is, so I should say I went to high school in the UK, not the US, so I don't know exactly what's in the curriculum here, but basically, if you can just get your like calculus down, like good step. I think you do that partly at high school and partly at university, right here. But that would be the one that I think people struggle with when they come into undergrad. So if you can get ahead of it, get on top of calculus as a high school student, that would be a good thing.
Yeah, I think calculus, it's starting to become a high school thing. At least in my case, next year I'm going to be taking calculus as a junior. Some of my friends are going to be doing it as seniors. So, yeah, that's just what I'm getting. Let's see. Many students watching this are passionate about science, but may not know the best way to turn that passion into a career. Let's talk about the path to becoming a physicist and the skills needed to succeed. In today's rapidly evolving world, dominated by AI and machine learning, many fields are seeing major transformations. For a high school student with a deep passion for core subjects like physics and mathematics, what career prospects do you see in these traditional fields? And how do you think advancements in AI and machine learning might influence or enhance opportunities in these areas?
Yeah, I mean, one thing that really is special about physicists is that they are always using the cutting edge technology to try and get this extra edge on nature. So whenever something new is born, like technologically, physicists are using it like right away. So like AI, we've been using AI in physics for like 20 years, like 15 at least, right? And so it's just a major part of our research already. Like my group, even before this big revolution in AI that happened recently, my group was writing papers and doing analyses using AI and machine learning tools. And these new breakthroughs that have happened with the large language models and everything are surely going to filter into advances in physics, and physicists will squeeze every ounce of out of those get more information about nature. So whatever the new technology is, physicists are using it to first order. And same with quantum sensing. I mean, physicists are really capitalizing right now on trying to use all the emerging quantum technologies for physics studies. AI, like you had this question sort of in there about job security. There is this transformation that's coming, right? That AI will make a lot of kinds of jobs redundant. In fact, the jobs that it will probably not make redundant are the ones which are based on conceptual understanding and deep conceptual analysis. I know there are some AI companies that create a lot of hype about these AGIs or concept models or concept learning. Personally, I think that's nonsense. I think that we know how large language models work. I mean, especially, physicists have been using AI forever. So as soon as ChatGPT came out, every physicist was like, I wonder how that actually works, and then looked up the details of how it works, right? Like all those things are doing is making a good estimate of what a smart human might say in response. So there was an example where I think, I don't remember if I think it was Elon Musk or someone typed in, like, give me some ideas about a quantum theory of gravity into one of these models. And back to the average person on the street probably sounded like, oh, that sounds like the sort of thing a physicist would say about quantum gravity. This thing must be really smart. But when physicists look at that answer, you're like, that's garbage. That's just made up, strung together. There's no insight there, right? So I think, for these fields like ours, where it's based on conceptual understanding, and actually building something to accomplish something, I don't think AI is coming for our jobs. I think AI for the job can be automated away because they're based on following a fixed sequence of instructions, right?
Can you describe the typical path from high school to becoming a physics professor?
Yes. So one thing I will do, I want to argue with the premise of the question a little bit, because I don't think anyone in high school should be thinking, I want to be a physics professor. I think people in high school should be thinking about whether they want to be a scientist, right? Because there's different ways of being a scientist. Like I'm one kind of scientist, but there are scientists at national labs. There are scientists working at IBM and NVIDIA, and there are scientists working at, SpaceX, or there's scientists working in all these different places. And really the path to becoming a scientist is the same for all of those paths. So you go to high school, you need to do well in your math classes. I would recommend, if you can, trying to learn a little bit about computers. If you have an opportunity to learn Python or some kind of programming, that's a great way to develop some early skills that'll set you up well for a scientific career. Then you go to do undergraduate. Pick a technical discipline. I mean, I would recommend physics. Physics definitely gives you the deepest insights and I would say the most transferable skills. So often people are thinking, I really love physics, but engineering maybe has better career prospects. Perhaps I should go in the engineering direction. One thing I'll say is, I mean, if you do physics, all the job opportunities in engineering will be open to you, because you'll have the skill set you would need to go that direction if you want to. So, pick a technical discipline. If you want to be a scientist, pick a scientific discipline. Don't be too intimidated. I mean, it is harder, I think, to get a degree in physics than it is to get a degree in some of the humanities and some other areas, but it's filling and worth it. Do study hard, do well in your classes, pay particularly close attention to the math-based ones, and then you would go to do a PhD. So in order to set yourself up for a PhD, one thing you can do as an undergraduate is get involved in research. So in my group, my research group at UTA, I have 5 graduate students who are people doing PhDs, and 10 people work with us who are undergraduates. They're just people studying for their physics degree. But in addition to that, they come in, they do paid work where they work in the lab, they contribute to our research projects. They have a small piece of the research project that's theirs that they have to solve. And it's a job, we pay them about the same as you would earn to work at Target, I guess, to contribute to the research. And they get to do that while they're doing their classes and everything. And then eventually, they get their name on papers. They've contributed to the research. They've really had a major impact on the way these experiments get done. Like our barium tagging work has a lot of input from undergraduates on it. And then if you get involved in that undergraduate research, then you'll be in a very strong position to apply for a PhD. And then a PhD is really where it's like a science apprenticeship, really where you learn to be a scientist. Now, one of the other things I want to clarify here is, because I think it's something that's often misunderstood, a PhD is a job. You get a paycheck and you have a contract and you work for someone who gives you stuff to do and you do science for money. I think, in England, I think that's more obvious where I'm from, right? We call it just doing a PhD. In America, there's this terminology, graduate school, which is what people call doing a PhD, which I think is a really unfortunate misnomer because it sounds like it's school. It sounds like it's, being a student, like being at high school, but it's not. It's a job. And so when you become a PhD student, then you're actually a professional scientist, right? But it's sort of that period when you have it's like an apprenticeship, and then eventually you do a PhD thesis and you get qualified to then be an independent scientist, not necessarily working for somebody who's telling you what to do all the time. So if you're somebody who is in high school and you want to be a scientist of any kind, follow those steps, right? Do well in your classes in high school, go to undergraduate, try to do research at your undergraduate. And when you're looking at undergrad places, you could ask them, what opportunities might I have here to do research? That's the way you might look at which university to choose. Anyone thinking about that might want to come to University of Texas at Arlington. We involve loads of our students in undergraduate research, and many of them then go on to PhDs at really prestigious universities like Yale or Columbia. But anyway, yeah, that's something you should think about when you're applying to undergraduate. Where can I get involved? Where can I do great research? And then, when you're in undergraduate, you'll have lots of advice given to you about how you might pursue a PhD after that. But then the last step, sorry, I know this is a long answer, but I think it's helpful for people to hear it. The last step of how you get to a professor, I mean, at that point, you'll know so much. When you've done your PhD, you'll know so much more about the field and about the different opportunities for being a scientist, either in the private sector or in academia or in national laboratories or for NASA or whatever. You'll have so much more understanding of all those things. It's really not worth thinking about that yet. Just think about becoming a scientist first, and then those opportunities will become clear, finding out from there.
So you mentioned like you're working with your graduate students. How much would you say they contribute? Is it is it kind of like equal, or are you doing most of the work? How is that like? How's that dynamic?
I think that the way I would say it works is that I generate most of the ideas, they generate some of the ideas. And in fact, the best ones are the ones who generate the most ideas. Like that's a really great graduate student who really engages with the problem, understands it, and is like, we should do it this way. And I have some that are like that, and they blow my mind how smart they are, some of them. But for the most part, the way it works is I have the ideas and kind of come up with the project ideas. And then I meet with a graduate student and say, I was thinking we should do this thing. Let's see how we can get it done. And then they go off and then try and execute that project, right? And I check in with them every few days and say, what's happening? How's the research going? We look at their system that's not working, or they can't get something to take data that's good, or they stuck on something. We solve that problem together, and then they continue working. So really, I'm sort of, I generate the ideas and then I offer tech support. And they're really the ones who are like doing the science. They're the engine that drives the research forward.
All right. What skills are most important for someone who wants to work in physics or a related field?
I think I said it already, but I think mathematics is useful, but not super abstract, high level math. Just basic like calculus, integration, differentiation. When you get to undergrad, it'll be matrices and differential equations. That's the level of math that you need. So undergraduate level math, coding. Like I think anyone working in any technical area needs to know how to code these days. In my group, we do almost everything in Python, but some C++. Like when you need to write a big software package, it's C++ usually, or when you just need to quickly get something done, it's Python. So I would recommend you learn Python and Python first, and then if you're really a computer nerd, then C++ as well. But you can learn that in grad school. You don't need to learn that. Python I would learn as soon as you can. And then, abstract thinking and a skill, to be honest, a skill that people don't emphasize enough, I think, is the ability to like really focus and concentrate on a problem. Because lots of people are interested in physics in the abstract sense. They hear something and they're like, oh, that's cool. I could imagine working on that cool sounding thing. I think one thing that people sometimes don't appreciate is to really become good at physics. You have to really spend time thinking about the concepts and figuring out how things fit together and making sure you have a sort of an intuitive picture of how it all goes together. And that requires concentration and sustained effort. So the ability to concentrate and sustain effort on a problem that interests you is another important skill, I think.
All right, now let's move on to your research opportunities for high school students and undergrad and all of that. How does the program engage high school students in nuclear physics research?
My group, at the moment, we don't have a formal high school student internship. We do sometimes work with high school students. Usually the way it works is that they, if somebody's really excited about working on science in high school, they reach out to us and they say, "Dear Professor, I love physics. I'm interested in your research. I wonder if there's any opportunities to do some volunteering work in the summer." And, I can't say yes to every person who says that because then I wouldn't have enough space in the group. But ultimately, if you're really passionate and you want to get some research experience, look up professors in the area who are near you and the ones that do the sort of thing that you're interested to do. Read about their research and then email them and see if there are any opportunities to volunteer with them. Sometimes people do it during the semester. More often it's during the summer. Actually, so far, the people who have done high school research with us, I think we've had 2. And then one of them went to Brown University to undergrad and the other one went to Yale. So it's a good thing for your CV to do. But again, I'd give 2 words of caution about that. Only do it if you really want to spend the time, right? You can't just go for an hour a week. You won't get anything. You have to really decide, this is my hobby. Other people are playing soccer or guitar or whatever, but what I want to do as my hobby is get into this for the summer, because you really need to spend the time to get somewhere with it. And in high school, it's difficult. So if you feel like that could be really exciting to you, then that's a good way to go. And then the other thing, I was going to email a professor. This is the number one tip I have. Never just email a professor and say, "Dear Professor blah, blah, I'm interested in research. Can I work with you?" You want to demonstrate to the professor that you've read about what they do and you think it's interesting and you've spent effort to engage with the material. So if you want to try and find an opportunity like that, write to them and say, oh, I heard about your work on the ice cube experiment, and I noticed you set new limits on sterile neutrinos. I think that's really amazing. I was wondering, are you still working on sterile neutrinos? And is there any way that I could help as a high school student, right? Like, it's a way you demonstrate to the person that you've really got that interest and commitment, right? Before they even meet you. So that's just good advice in general when emailing people about careers and jobs and things.
What's the most rewarding part of mentoring young scientists, and how has it impacted your own career?
It's amazing, honestly. It's one of the best parts of my job. To work with people who really care and really want to develop their skills, develop their understanding. And, I feel like when our group is working at its best, it's when it just feels like we're a team, right? We all want to succeed. We all want each other to succeed. The junior people want the senior people to succeed, and the senior people want the junior people to succeed. No, I find it really, really rewarding to watch people grow and accomplish things as young scientists is great.
So for your program, where can interested students find more information in order to apply?
Well, if you are interested in my research, the best thing you can do is apply to UTA to be a physics major, and then come and do research as an undergraduate researcher with me. And like I say, I can't take everybody who expresses an interest, but the people who are really keen, generally get a shot. So if you'd like to work on the things I work on, apply here, graduate here, and then write me an email and say I'd like to do research with you. That will be my recommendation. It doesn't have to be at UTA. There are other universities on the market that call to you. You can often find research opportunities in this area in other schools as well.
Yeah, now let's move on to the future of the field. So Microsoft, I don't know if you've seen this, but Microsoft recently announced the development of the Majorana 1 chip, which uses a new state of matter known as the topological superconductor. And this breakthrough, right, it enhances the stability and scalability of qubits in quantum computing. So with your expertise in neutrino physics, could you explain what the impact of this might be in the future of quantum computing?
Yes, absolutely. Sorry, did you have more?
No, you're good. No,
okay.
Yeah.
I do have expertise in Majorana particles, right? And I also have expertise to some extent in quantum computing because I've written papers on quantum computing, and I also have expertise in these kind of quantum devices. So this is an area which I do follow. I think that one of the things that's kind of interesting about the quantum computing field right now is the way it's being driven by capital rather than fundamental science, right? I mean, Microsoft is a big company and they're competing with Google, which is a big company. And it's interesting when these breakthroughs happen, quite often the scientists of those places, they write a paper, which is actually a perfectly well-written, reasonable scientific paper, and then becomes subject to peer review and debate in the literature, and people argue and test, But at the same time, then the company, the press release people, make some wild press release that says something crazy that the paper doesn't say. So this one, I saw the press release said something like, Microsoft invents a new state of matter that will revolutionize quantum computing and drug discovery. None of the scientists who actually worked on this said that, right? That's just Microsoft saying. And similarly, I think Google had one recently where they said that Google had proven the existence of parallel universes or something, which was also false. I mean, it was just the company making a statement that was scientifically unjustifiable because they need that kind of statement for their investors, right? Now, what's really happened here is important and could be a breakthrough, which is that Microsoft has been working on this kind of qubit, which is different to the ones that other people work on because it's based on this topological state of matter. So it's harder, but if they succeed, then this qubit will be much more tolerant to loss of coherence than other ones. And work is fabulous, and the progress they're making is impressive. The paper they wrote was that they had demonstrated a very specific technical advance, supposedly, which I won't describe in detail, but it's an important one. I mean, it's an important step towards this being a viable technology. Now, they haven't completely solved the problem, and they have definitely not done what it said in the press release, which is invent a new state of matter that can enable quantum computing. And furthermore, the step they've made, the technical step, is now, like everything in science, is now subject to review by the rest of the field. So it now requires other scientists to scrutinize the paper. I saw there was a paper recently where somebody had written a long criticism of some of the techniques that were used in the analysis. Now it's up to Microsoft to respond to that criticism and convince people that they know what they're doing. This is the scientific process. And really, this is what's supposed to happen. You're supposed to produce a result, and then everybody in the field is supposed to scrutinize it and figure out leave it. And then you come to a consensus in the end, right? When you've all argued it out and investigated it from every angle. A part of me does worry a little bit that if we let science be concentrated by major companies, because so much of their technical work is protected behind non-disclosure agreements and paywalls and corporate iron curtains, that it will be difficult for people to really understand whether these breakthroughs have indeed been made or not in the way that we would expect to as scientists. At least in this case, I've seen that there's been public discussion about what these results mean, and presumably Microsoft will do further work to respond. And I hope as much of that as possible is conducted out in the open as we expect science to be conducted. But that was a long answer, but that's my feeling about it.
Yeah, I didn't actually know that it was under scrutiny. I was just getting like kind of articles saying like, oh, there's this major breakthrough. So that's interesting.
Yeah, when you're looking at those pieces of news, one thing I'll mention, if like a major scientific experiment like LIGO or the Large Hadron Collider or IceCube or something, if they announce the discovery of something, I mean, you should still treat it with caution, because like the whole point is they'll announce it and then other people will try and validate it, argue about it, peer review it. That's all part of the process. But I will say that those collaborations generally are not trying to please like investors and who are investing billions of dollars in development of the technology, right? They're trying to make the measurements for their own sake. And so they're much less likely to come out with something that's like underbaked and hype it, right? When it's companies, like you should treat it with some suspicion, because they need to generate more revenue, right, for investment in their work, and more of a tendency to create hype about the things.
All right. So, where do you see your field heading in the next 10 to 20 years? What emerging trends excite you the most?
10 to 20 years. So, hopefully in 10 to 20 years, we will have, in neutrino physics, we will have at least one ton-scale Neutrino-less double beta decay experiment, which, whether the neutrino is Majorana, and possibly discover a Majorana neutrino. We should have 2 experiments that are able to tell us whether the neutrino violates CP symmetry, which means whether in the leptonic part of the standard model, matter behaves differently to antimatter, which is also connected to this mystery of matter-antimatter imbalance. We will have new dark matter experiments, and we will have upgrades to the Large Hadron Collider. So there are many programs that are making important advances. The thing that's really interesting is to wonder what are the unexpected breakthroughs that are going to happen, right? Because those are the ones I expect. But the ones that are the most interesting are the unexpected ones. And if I had to guess, I would imagine that if we keep seeing major emphasis on quantum computing and quantum sensing, that we will have new technologies emerging as a result of that focus on quantum instrumentation and be profoundly more sensitive to small scale effects than our classical technologies, and possibly also even give us some more insight into these mysteries of quantum mechanics like the observer problem. But again, I predict that because no one knows how those kind of advances come about. But that seems to be an area where there's like really rapid progress right now, and I'm watching it with great interest.
You mentioned quantum computing. I don't know if this is like a real possibility, but in how many years do you think like quantum computing will become like the new like just regular computers, and like you might see it in like homes?
That's an interesting question, because I think it will never become that, because quantum computing solves a different kind of problem to normal computing. right? So normal computers are very good at doing the kind of hyper parallelized, many calculations in quick succession kind of computing that we do now. Like you wouldn't want to run like a web browser on a quantum computer, right? Like what quantum computers do is they can solve in principle problems that classical computers find very difficult. So, factoring large prime numbers is a famous example. Like classical computers, that takes forever. But on a quantum computer, it can be very fast. And there are other problems like that, like simulating quantum systems or solving very large combinatoric problems. Quantum computers, in principle, can advance those specific problems. So I'm not sure if they'll ever just become part of the standard desktop PC. It's more likely that they will become available for very specific, complicated kinds of calculations that will let us then advance our understanding of things.
Last few questions. What legacy do you hope to leave in your field, and how do you want to impact the next generation of researchers?
Legacy. Okay, so science these days is sort of a coral reef, right? Everybody puts a piece on, and then eventually there's a reef, right? Not quite the same way it used to be in the old days, where like one person would just like write the paper that revolutionizes the entire field. And in a way, it's good. It's because we not only have solved a lot of the easier problems, but we've got a much wider array of questions that we're asking than they used to be asking in the old days, right? With all the science, we have many more directions to ask questions. So, I think my goal really is to do work that's creative and impactful and leave something on that coral reef that like wouldn't necessarily just have been left by somebody else if I wasn't around, right? So to me, really, it's about creativity. It's about trying to synthesize ideas in ways that other people wouldn't necessarily do, seeing where that goes, right? So if I can leave a couple of really creative and interesting new directions, like on the coral reef, I think that would be a good goal.
Finally, let's end with some words of wisdom for students who dream of a future in science. What one piece of advice would you give to students who dream of making a difference to science?
One piece of advice, I think I would say, there's no such thing as intrinsic intelligence. There's just how enthusiastic you are and how hard you work. If you're enthusiastic, you dig in, you study, you work, you can figure it out. No matter what the super hard maths, super hard physics, super hard computer problem. If you're excited about it and you work hard enough, you'll figure it out.
All right, Dr. Jones, thank you so much for doing this interview. This was a blast. Hope you have a great day.
Great. It's been a pleasure. Thank you very much.